Hello, gentlemen. This is a continuation from our last or first example in balancing chemical equations. We're going to continue with example 2. Now, this example seems a lot more complicated or complex because there are more atoms involved. But right now, we're going to go through a different way to balance your equation using what we call clusters, or creating a group of atoms as one unit. Now, this can happen when we look at our certain chemical equation when we notice certain trends or certain similarities. Here I have potassium chromate reacting with lead 2 nitrate, yielding potassium nitrate plus lead 2 chromate. Now, I said nitrate and chromate a few times there. Let's talk about what those are. Now, we notice CrO4. This appears the same way here in our reactant side and in our product side, CrO4. Since they appear the same, we can treat them as one unit. So this would be a cluster. So I would take this CrO4, treat that as one unit, and this CrO4 as one unit. I also have NO3 here. It's the same NO3 as the NO3 on this side. So I can use this NO3 here and this NO3 here and treat them as one unit. Now, just like any other balancing problem, I'm going to list what I'm going to need to balance. List my atoms. So, first thing is this marker. I have my potassium atom. How many potassiums do I have on this side of the equation? I have a 2 here, a subscript 2, so I only have 2 atoms. Next, I have this unit here, the CrO4. Because I have the same thing on this side of the equation in a cluster, and the same thing on that side of the equation in a cluster, I can keep it all as one unit, meaning I can write it all as CrO4. Instead of writing Cr here and then oxygen down below it. I can just keep it all as one unit. And how many do I have? I only have one of them. Moving on to my next chemical formula. Lead. Pb is lead. I only have one of them, so for Pb, I only have one. Now I come to this NO3. NO3, we keep it as one unit because we have NO3 over here and we have NO3 over there. Even though this one's in parentheses and that one isn't. They still are counted as one unit. Now, this one unit here, because it's in parentheses and there's a 2 outside, this 2 is kind of like a multiplier as well. It says that I have 2 units of NO3. So these parentheses act as kind of describing something as a quantity. I have 2 of this quantity, just like if you were in algebra class and you were distributing into a parentheses. So I have 2 NO3 groups. Now on my product side, same ordeal. We cut our atoms up. For potassium, I have 1. For chromate, which is CrO4, I have only 1 chromate there, no parentheses around it, with the number outside, therefore we just say it is 1. My lead atom, I only have 1 as well. And for my nitrate, I simply have 1 because it's not surrounded by any parentheses. Now, with these clusters, it's made my atom counts really simple. 1, 1, 1, 1, and 2, 1, 1, 2. That's pretty simple. Otherwise, if I had put my chromate and oxygen separate on either side and my nitrogen and oxygen separate, I would have had much larger number of atoms. So let's balance. I have 2 potassiums on this side. I have 1 potassium on that side. Let's balance my potassiums first. I want to put a coefficient in front of my potassiums here to make it up to an atom count of 2. So I put 2 there. 2 times my 1 potassium takes away my first one, but I have 2 now. Okay, but this 2 also applies to this unit of NO3 here. 2 times my 1 NO3 unit gives me 2 NO3 units. And what do you know? This balances to the other side already, just with this one coefficient. I have 2 potassiums, 1 chromate on either side, 1 potassium, and 2 nitrate groups on each side. 2. Now this equation looked very intimidating at first, but it only needed one coefficient. And it was easily recognized because we kept our atoms in clusters if, and only if, they look the same on both sides of the equation, exactly the same. That's example 2. Example 3. This is an example of a combustion reaction. I have propane gas reacting with oxygen gas, yielding carbon dioxide gas and water vapor. Now, to start my balancing, I just list my atoms as always. I have carbon, hydrogen, and oxygen. For my carbons, I have 3. For my hydrogens, I have 8. For my oxygens, I have 2. Other side, carbons, hydrogens, and oxygen. For my carbons, I have 1. My hydrogens, I have 2. My oxygens, I have 2. Plus the 1 over there, it's a total of 3. Now, since my products of my combustion reaction are always going to be carbon dioxide and water, my atom count for a combustion reaction on the product side will always be 1, 2, 3. It's an easy thing to remember, a good, a good note to have. Now I want to balance. When it comes to combustion reactions, we always want to balance in a specific order. We want to balance the carbons first, hydrogen second, oxygens last. Let's try that method. So my carbons, I have 3 in my reactant side, 1 in my product side. I'm going to need more atoms of carbon in my product side. Thus, I add a coefficient here. I'm going to add a 3 because I want 3 times my 1 carbon to equal 3 atoms of carbon. But this 3 also applies to the oxygen behind this carbon in my carbon dioxide formula. So 3 times the 2 oxygens that I have here gives me 6 oxygens plus that 1 oxygen that I have over here. So 3 times 2 oxygens is 6 plus the 1 is 7. My carbons are good. Everything else is coming along. Hydrogens. I have 8 hydrogens here in my reactant side. I have 2 here in my product side. I need 6 more over here in my product side. Thus, I go over here to my hydrogens and I think what times 2 is going to give me 8? Sure enough, you know that's 4. 4 times my 2 hydrogens gives me 8 hydrogens, and there I am right now. So I have my carbons, which are 3 and 3, hydrogens, which are 8 and 8, but the addition of that last coefficient here, 4, changes my oxygen count. I have 4 times my 1 oxygen, that gives me 4. And I can't forget these oxygens over here. I have 3 times my 2 oxygens, that gives me 6. 6 plus 4 is 10. So I no longer have 7 oxygens, I have 10. Now I have to go over on this side and balance my reactants, the oxygens in my reactant side. So I have 2 here. So here in this spot, I'm going to say what times 2 is going to give me 10. That is the coefficient of 5. This is a balanced chemical equation for the combustion of propane gas. Hope you learned a few things. Hope this helps. Gentlemen, study hard.